So we're going to go a little bit kind of old style here, and we're going to start taking some notes on some of the paper that I was telling you earlier Mary was trying to get me to use up. Unfortunately, my camera is being slightly difficult. Let's see if that helps. Okay, so we're going to start talking about tangent lines here. When we're talking about tangent lines, you're going to need some materials. So, honestly, you need a ruler. Get yourself a ruler. And then you're also going to need a compass. Now, I modified my compass a little bit so that you could see it. If you don't have a compass, then you probably need some circular object or maybe another circular object. But you're going to have to be drawing some circles because we're talking about tangents. So first thing you should know is kind of the definition of what a tangent is. If we have a circle, go ahead and give yourself a nice, big old beautiful circle there. If we have a circle, any line that is tangent to the circle is a line that touches the circle, if you will, in one place. So I'm going to go ahead and mark my line along through here. And you can see that my line is a straight line that is touching that circle in one place. As always, let's give them some good names. So we know that in this circle, in combination, oh, I forgot, this is my circle, and it's called circle D. So here, this circle gives us a tangent line, here A to B. And this is called, like we said, a tangent. And it has to touch that circle in one place and one place only. The second thing that we should be worried about is this point right here. And we call that the point of tangency. I know, fancy, right? Super exciting. There's lots of theorems that we're going to talk about when it comes to the tangent lines. I think there's about 6 of them in this chapter. The one that is important to us today at this exact point is the theorem that tells us that that point of tangency, no matter where it is on the circle, is perpendicular to the radius. So it does not matter at all where I draw my point or my tangent line. Wherever I put in my tangent line, it will be perpendicular to. So there's a new tangent line. I call that one XY. And that one will also be perpendicular. We can find our little point. Right there is exactly where they touch. And when I connect that radius from the center of the circle to that point, it forms a right angle. So I like to have all of my theorems in a nice handy dandy little card here. So you'll notice I've made myself a yellow card, and it simply states that if line AC is tangent to circle O at point P, then AC, which is the line of tangent, or the tangent line, is perpendicular to the OB. So when we're looking at this, we just know that the original theorem is that the radius and the tangent line form a right angle. Now the opposite of that is also true. I like to put my converses on the back of my cards. If you guys would like some cards, you can go down and borrow them from Mary. Miss P might have some on hers. I like to write this as short as possible. If line AC is perpendicular to OB, then AC is a tangent to the circle at point B. So it's both of those. If it's a tangent line, then it's perpendicular, and if it's perpendicular, then it's a tangent line. So let's talk about one of the first types of problems you might encounter when you have tangents to a circle. You can notice here that I have my circle O, has a center at point O, and then it has a point out here in space labeled M. Then it has 2 tangent lines, one at NM and a second tangent line at LM. And we know that both of those are tangent lines because it was given to us. The question for us becomes, solve for x. Now in doing so, you need to pull a few things that you might remember, right? First, we know that tangent lines, based on our theorem from this unit, we know that tangent lines are always perpendicular to the radius of the circle. So that means when we're looking at our tangent lines here, the radius is here, the tangent line is there. That must be a 90-degree angle. It has to be. Same on this side. But now it becomes a simple solution for our problem. So we start off with, this is a quadrilateral, right? M, N, O, L makes a quadrilateral. And so you know already that the measure of the interior angles of a quadrilateral is 360 degrees. Just like a triangle is 180, quadrilateral is 360. So now I can simply take this and add the measure of my angles to equal 360. So 90 degrees plus 117 plus 90 plus x equals 360. Simple quick calculator work. You can turn around and add them all together if you want, or you can subtract them each on either side. This means that 297 degrees plus x equals 360. Subtract 297 on both sides, and then we know, I'll write it out for you, that our x equals 360 minus 297, which is 63 degrees. And usually we write that as the measure of angle x. So for this, we're at 63 degrees. Here we are again. We can use our tangent principles to also find or solve for the radius of a circle. In this instance, you can see that AB is tangent to our circle C. At the same time, we see that there's a point in space A, which is connected to C, center of the circle, and it has a partial distance of 8. The first thing that I'm hoping you should recognize in this, that the distance from C to B is the radius, and that's the same distance no matter where on the circle the point lies. So the distance from here to here has to be the same from there to there. So they're all equidistant. The second thing that you should realize is, since AB is a tangent, we know that it makes a right angle. So because AB is a tangent, then therefore it's a right angle. Now, one of my favorite things about right angles is that they form right triangles, and it opens up for us to use the Pythagorean theorem. You'll remember looking at this that our hypotenuse is here from AC, and then one leg is AB, the other leg is CB. And you should remember without a second thought, our Pythagorean theorem tells us a squared plus b squared equals c squared. And c is always the hypotenuse. So our a side is x. It's right there. Our b side is 12. And our c side is the hypotenuse, or the length of this side. Now this isn't just a straight number and super easy. So this distance is x plus 8, which we have to square. So here we have x squared, which stays the same. 12 squared becomes 144. And this piece, x plus 8 squared, we're going to have to factor out on our own. So I'm going to put a sticky over here to do that math. Remember, this means this. X plus 8 times x plus 8. And when we're doing that math, we have to use that FOIL method. First times first is x squared. The outer terms times each other are plus 8x. The inner terms are also 8x, because 8 times x, and then my last term is 8 times 8, which is 64. Now I'm going to combine these center terms together because they're the only two that have just standard x with no square. So this becomes x squared plus 16x plus 64. So I can replace that then on this side of the equation, the x plus 8 squared with x squared plus 16x plus 64. Now I need to solve for x, and in doing so, I need to collect all of my terms on the same side so that I have variables on one side and coefficients on the other. So in this case, I can go ahead and take my x squared and move it to the other side. Remember my brother and sister rule, whatever happens to one side happens to the other, and then those will cancel out. I should then rewrite my equation. Notice I now have 144 equals 16x plus 64. Then I'll go through and subtract to get the x by itself. So I'm going to go ahead and move 64 to the other side. And I'm going to do, that was like a mini earthquake right there. So I'm going to go ahead and clear that out and just use my calculator so I don't make any mistakes. 144 minus 64, and that will give us 80. And then the 64's cancel out. I'm left with 16x on that side. And then to solve for x again, I need to use my opposites or inverse relations. So I'm going to divide both sides. My 16's cancel out, and 80 divided by 16 is 5. So going back to the problem now, we see that the radius of this circle is 5. The last theorem that we have in this section we're looking at is the theorem that talks about two tangents. And what it tells us is that if you have a point outside of the circle and there's two tangents which come off of that point and touch your circle. So we have two tangents that are tangent to the circle O and they intersect at a point B here. If they're both tangent to O, then those two are congruent. It makes it a lovely setup when we're solving for triangles, which you guys will see in just a second. It's, like I said, very simple. Our two tangents theorem is right here. Like I said, I like to put mine on separate cards. It gives me my drawing, tells me that two tangents. If line AB and AC are tangent to circle O, then BA and CA are congruent. So let's take a look at what that looks like in real life. So on this one, we're going to do some really difficult straight-up addition work. So when we're looking at this, it asks us to find the perimeter of triangle ABC. Knowing that it's inscribed inside of that polygon is this circle, we'll call it O. For some reason, we love to call circles O. So for circle O, we want to be able to decide, using our tangents theorems, what the perimeter of ABC is. So when we first look at this, we should recognize that here we have a point in space, and that from AF and AD, that these are both tangents to this circle, which means that if we have two tangents to a circle that intersect in one point in space, we know that those two tangents are equal. AD is 10 centimeters. That means AF must also be 10 centimeters. We can take that same principle over here to our B corner, and if we notice BD, which is a tangent to our circle also, is 15, that means BE also must be 15 centimeters. And then lastly, down here at this tiny little point at the bottom, which is our point C, we're going to want to take that same piece and look at our 8 centimeters for CF. That means that since they're both tangent to that circle O, CE is also 8 centimeters. Now we can use that incredibly complicated segment addition postulate to know that we can take segments and add them together in order to get a perimeter. So 10 plus 10 plus 15 plus 15 plus 8 plus 8. And when we add them all together, we should get a grand total of 66 centimeters for the perimeter. Like I said, some difficult math work there, right?